and Starlab organizing team to invite all of you and to welcome all of you to our workshop today, which is focused on technology for health in space. This is part of an ongoing workshop series, which if you'll give me a moment, I will screen share to showcase the rest of our workshop series. So this is part of an ongoing 6-part workshop series that the Human Performance Collaborative and Starlab are running together, exploring and digging into various topics in bioastronautics, which includes technology for health, microbiology, immunology, and health in space, habitats and habitat development in space, space medicine, space psychology, and advancements in space training. The intention behind this 6-part workshop series is to intersect academic and industry researchers and to hopefully spark some conversation, some new ideas, and some maybe exciting partnerships in the future that will help us to progress space research across all of these fields. As you can see here on the screen right now, the workshop is hosted mostly virtually. We will have one in-person workshop, but it's mostly virtually hosted in order to allow our friends and collaborators from all around the country to join us in these sessions. The workshop lives on the HPC website here. So if you are looking to join in on future workshops or to share this around, this will be where all of the information for that will be posted. Today's run of show is going to include a brief introduction to Starlab, an introduction to the Human Performance Collaborative by Dr. Josh Hagen, and then 4 fantastic panelists, each of which will give an approximately 15-minute presentation about their research work and such in space research. And then after that, we will have a moderated panel that will include opportunities and times for anyone, any of our participants and audience members to ask questions and engage in discussion with our panelists. So without any further ado, if you'll give me a moment to get my screen share set up, I will jump into giving our Starlab introduction. For some people, you may already be familiar with Starlab, but I know that we likely have many people joining us today who are new to our Starlab initiative, so I will try to not dig into too many of the nitty-gritty details and instead give an overview. But if anyone is interested in learning more about Starlab after the fact or discussing ways to become involved with us, please reach out to me. My contact information is included on the last slide, as well as all over on the instructions for joining the workshop and such. So please feel free to reach out. So the Starlab Space Station is a collaborative project. The Starlab Space Station is one of the next generation space stations being developed to take over our human habitation and research capabilities in low Earth orbit at the end of this decade, when the International Space Station, which has been our home for human habitation and research for the last 25 years, is decommissioned and brought down. Starlab was initially developed under a commercial low Earth orbit destinations award from NASA, and has grown into a fantastic joint venture with partners from all over the world who have long histories across many different disciplines of space research and operations, including Voyager Technologies from the United States, Airbus from Germany, Mitsubishi Corporation from Japan, MDA Space from Canada, Palantir also from the US, and Northrop Grumman. The Ohio State University is the lead research partner in the Starlab joint venture initiative, helping to develop research pipelines for microgravity and low Earth orbit research that will be hosted upon Starlab and hopefully other stations in the future as well. A couple of details about Starlab. So externally, there will be opportunities for externally hosted payload platforms, as well as a large science airlock to allow for transition of platforms internally and externally, and a robotic arm developed by MDA, who are the makers of the Canada arm that is currently on board the International Space Station. Internally, Starlab is composed of 7 decks, with 3 of those decks being habitable and living quarters where research, habitation, and other human factors are allowed, and 4 of the decks being stowage, subsystems, power distribution, and life support. The internal capacity of Starlab is approximately 1,500 square feet. That's only the habitable area. We will have 130 mid-deck locker equivalents for internal research payloads, built in a modular and flexible architecture to allow for differing arrangements as needed across the lifespan of Starlab, with full laboratory capabilities for pretty much everything that you could want: glove boxes, cold stowage, workbenches, and other microscopy and advanced techniques to do the full process of research within space.
Hey, Abby, I think we might need you to change your slides. We're just seeing the title slide.
Oh, shoot. I'm so sorry about that. On my side, it's been flipping through, but I think, thank you for letting me know. I appreciate that. Let's see if this works better. Hold on just one moment.
I thought it
Bear
was
with
just
me.
me.
Thanks, everyone, and I apologize for that. That's appreciate your patience as we run our first virtual event of this series and work out some of the kinks of operating. Okay, can you guys let me know if you're seeing flip through of slides now? Okay, amazing. Thank you so much. Let me go ahead and put that into presentation mode. Okay, are you still seeing flip through of slides? Beautiful. I'm going to just zoom through the ones that we've already covered and showcase. Essentially here we can see the various partners that I described who are a part of the Starlab joint venture. We are really proud of the fact that we exhibit the global contributions through our partners. That is a heritage element that worked so well on the International Space Station, and that we're building a station that is accessible and applicable for research communities across the world. Here's the external areas that I was talking about, where we'll host external payloads with our robotic arm, science airlock, etc. Our structure: 3 habitable decks, 4 non-habitable decks with support services housed inside of them. The internal components, where we have approximately 1,500 habitable square feet and 130 MDLE capability for internal payload hosting. Okay, now we get to jump into some of the new stuff. So one of the things that I want to highlight about Starlab is that we are building Starlab in a terrestrial ecosystem that includes both Starlab itself as our on-orbit platform, but also research centers and science centers here on our planet, including science parks around the world, such as the Voyager Institute for Space Technology and Advancement, which is the world's first space-focused science park that is being constructed right here on the Ohio State campus, as well as partners with UTH Zurich and a couple of other iPark in Japan, as well as hopefully future partners around the world. We're also including universities and national space agencies as terrestrial partners within the work that will be conducted on Starlab, and are excited to integrate and work with researchers across all academic, industry, and government sectors of space research. Currently, this showcases the international partners and collaborators that we have involved in Starlab, and it's my hope that we'll end up seeing a lot more purple on this map as we continue to progress down this path towards our launch date in 2029, when Starlab will become operational in low Earth orbit. And then I did just want to highlight and mention our collaboration with Palantir, who are helping to build the AI backbone of our station that is so important for both our customer integration and database, and also our on-orbit operations model. And the reason I want to highlight this today is that we're going to be talking, hopefully some of our speakers, I believe, will be talking about the utilization of analog and digital twins in space research. And in this, we do have a digital twin that is being built of Starlab that allows for our research management and increased efficiency of operations on the station as we balance the needs and priorities of many different customers and partners who will be utilizing this research space. Just really quick, I figured we'd go through for some of our attendees here who may be new to what space research looks like, what that pathway from ideation all the way to proven and flown flight looks like. So the very beginning, as with most research, is the design and the acquisition of funding for a space research project, safety approval, where you'll work with Starlab and our partners to determine the best practices to get your work to space, building and testing of your payload, transfer of payload to our facilities, and then launch to the station, operations, and then finally the return and disposal of any research products after the fact, whether that be actually returning of samples or more efficiently, the returning of information from work that has been conducted in space. And I'm sure that we will hear more about this research process from our panelists today who have some significant experience in conducting space research themselves. And finally, I appreciate all of your patience as we worked through those technical issues earlier. If you have any additional questions about Starlab, our operations, or would like to discuss further how to become involved with us for in-orbit space research, please don't hesitate to reach out to me, and we can have a conversation and get all the right people connected there. So with that, I will pass along the baton to my colleague, Dr. Josh Hagan, to share more information with us about the Human Performance Collaborative here at OSU, who have been continuing fantastic partners in our efforts to increase human research in space. Josh, the stage is all yours.
All right. Can you see my one slide? Yes. Okay. Cool. I can't see anything. So we can figure out how to get to space. We just can't figure out how to use PowerPoint. At least I can. But welcome everybody. Really excited to have you here. This series of workshops is super important. There's just so much exciting work happening right now, and all things space research, especially at Ohio State and the Starlab, that we're extremely excited to be part of. It's just starting. There's going to be so much awesome work going on in the next decade plus. We at the Human Performance Collaborative we're a pretty large entity within Ohio State, and really our objective is to create really large, amazing multidisciplinary teams across Ohio State, but across industry, across other academic institutions, across the DoD, government, NASA, everybody. And our mission is we want human beings to optimize their performance, no matter who it is. So whether it's astronauts, whether it's inhabitants of the space station, whether it's the crew on the ground that are taking care of all of these people, like every single one of these human beings can be optimized. And we're creating tools with the HPC to really understand what optimization means. Like we're all human beings. So it's all physiology. It's all, it's a really exciting time for a lot of technologies and advancements that we have in human performance. So putting those philosophies and mentalities together with all the awesome work happening at Starlab and space research is really going to be super fun over the next decade. So I appreciate everybody's involvement. Thanks for being part of this one. Sign up for the next ones. These will be great. And sign up for research at Starlab, be part of Starlab, be part of HPC. Anything you need, reach out to us and be happy to chat more. So thanks a lot. And Abby, I'll hand it back over to you.
Fantastic. Thank you so much, Dr. Hagan. And I have to say that I learned from your example that one slide is a way to avoid any problems. So
I still almost messed it up though.
With that, I will go ahead and invite our first speaker, Dr. Lauren Merkle, who is the Collaboration Director for the Health and Human Performance Contract with KBR. Dr. Merkle, we're so grateful for your generosity in sharing your time and expertise with us today. And I won't spend any more time yapping. Instead, I will hand the stage over to you and listen raptly to your presentation.
Right. Well, hopefully you guys can see slides. Yes? And you can hear me. Great. Okay. All right. So thank you very much for the invitation. I appreciate you guys working with us. I was invited to talk to you a little bit about what we do here at KBR in the Human Health and Performance Contract. You see the number 2 there. This is the second HHPC. We started HHPC2 about 2 weeks ago. It's actually on November 1st. It is actually work. It's a contract that we've held for well over the past 40 years. So it says HHPC2, but this contract has had a lot of different names. But essentially, what I thought I'd talk to you guys a little bit is give you a nice overview of what we do. Talk to you about our TechNet, which is something new that we've established for this brand new contract, and Ohio State is on that list, and then some of our strategic priorities. So basically, the big picture is our job at KBR and on HHPC is to enable humans to live, work, and thrive in space. Historically, that has been the space shuttle program. That has been until about 6 or 7 years ago. That has been the International Space Station. But with the onset of commercial crew about 6 or 7 years ago, and of course, our Artemis missions to the moon, onto Mars, and beyond that, that has expanded quite a bit. And we anticipate the scope of this contract is going to be quite different. Historically, certainly for HHPC1, most of the contract was normal standard ISS operations and standing up the commercial crew program. And what we're doing on HHPC2 is going to involve a change in platform. Abby talked about ISS being decommissioned. That sunset should happen in about 5 years. But the other thing that's really, really changed over the past 6 or 7 years is the idea of a global space flight economy. When we started HHPC1, that did not exist, and NASA was the only game in town. If you wanted to go to space, NASA was it. But now we have a global space flight economy. And what we want to do on HHPC2 is be the group that leads that spaceflight economy in protecting crew health and enabling human performance. Our job is to support astronaut health, ISS, commercial crew, Artemis. And that's everything from crew selection all the way through an astronaut's lifetime. That also includes occupational health on the ground and performance optimization of NASA personnel. KBR operates the clinic that's on site at Johnson Space Center, as well as the clinic at White Sands Test Facility. And anyhow, we do a lot. And we also want to make sure rocket science is certainly difficult. But it becomes exponentially more difficult when we add a human system to that. And so our job is to make sure that those crews stay healthy and we have mission success. HHPC2, much like HHPC, Bioastronautics, and the MISSIC contract before that is a 10-year contract. Like I said, we started November 1st, so past couple of months have been a little sporty. But it's a 10-year contract. We'll be doing this work through October 2035. We have about 1,000 employees, and we do work here in Texas, at White Sands, in New Mexico, in Star City, Russia, and at NASA headquarters in Washington, D.C., at Marshall Space Flight Center in Alabama, and the Kennedy Space Flight Center in Florida. So we're all over the place. I could spend the whole 2-hour workshop talking about what we do on HHPC and what KBR does for NASA, but we just don't have that time. So I'm going to squish it down and give you the 30,000-foot level. So if I were going to put it into just a handful of words, we put the human in human spaceflight. That is what we do. If it touches the human, it's something that we do. Everything that we do on this contract is looking to mitigate human system risks. Of course, we know that as humans have evolved, we've evolved with a gravity vector. Our world is a very definite up, down, left, right, front, back. When we get to space, those coordinates don't necessarily have a whole lot of meaning. And there's tons of physiological changes that happen when we put humans in space. And so at a very high level, our job on this contract is to mitigate these human system risks. And that is defining and identifying and developing countermeasures for the physiological changes that take place. So things like balance disorders, fluid shifts, changes in the structure and function of the eye, cardiovascular and musculoskeletal deconditioning, bone loss, those kinds of things. Space radiation is something that we're certainly concerned with and have been concerned with for the shuttle and the ISS programs, and those risks are pretty well defined. We know that the crew are at increased risk for the development of cataracts and certain kinds of cancer based on their radiation exposure. But the fact is, when we start going to the moon and going to Mars and getting beyond the Van Allen belts that that do provide some protection for radiation, this risk is going to change. Isolation and confinement. The behavioral and team aspects of spaceflight are extremely important. Our crews are selected well in advance of any particular mission, and those crews train together on an average of about 2 years. When we start flying to places like Starlab and other commercial space stations, those dynamics are going to be different. We may well have people, we may have NASA astronauts flying with commercial astronauts who are also flying with space tourists or, you know, those kinds of things. And so we have people who'll be flying with people that they have not necessarily trained with. And there's also the aspects of sleep disorders. Crew experience on the order of 16 sunrises and sunsets. So we all recently experienced the end of daylight savings, and we know how much that 1 hour did to us for a week or so. So the crew definitely have disordered sleep, disordered circadian rhythms, and our team works really hard to make sure that the crew gets the best rest that they possibly can. The hostile closed environment, we're involved in vehicle design, making sure that all of the habitability systems are working. We're involved in displays, in guidance and navigation, in any sort of environmental or toxic exposure. The International Space Station is cooled with anhydrous ammonia, and we know what that spill did in Oklahoma earlier this week. So all those systems we're responsible for, including water, nutrition, food for the crew, managing their changes in immune function. We know that crew experience increased shedding of chickenpox, live chickenpox virus, even though they're vaccinated and maybe are not showing any symptoms. And of course, microbiome changes, and then of course, distance from Earth. As we get further and further away from Earth, having the crew be able to have autonomous medical care, autonomous decision making, because they cannot come home. Right now, with the International Space Station, if there is any sort of vehicle or medical emergency, we can have them home within a couple of hours, probably at longest 24 hours. When we go onto the moon and Mars, those kinds of returns are not going to be possible. So we want to make sure that the crew can function as well as they possibly can. So we have, I'm not going to read all this. We have four departments that align with NASA's Human Health and Performance Directorate. So we have an enormous biomedical and environmental research area that studies everything from cells to human systems to the entire human, anthropometry, biomechanics, suit and glove fit, changes in systems, EVA physiology, nutritional biochemistry, tissue culturing, air and water quality. We do space medical operations, which means all the flight surgeons are ours. So we do flight control support for mission control, flight surgeons and biomedical engineers, behavioral health and psychological support for the crew, as well as their families, epidemiology, because we follow all of the astronauts from the time they are selected all the way through the end of their lives. We have their athletic trainers, their strength and conditioning specialists, industrial hygiene, launch and landing support, and we support the NBL, the Neutral Buoyancy Lab. We have a huge engineering department. So any of the flight hardware that the crew have to touch, we are involved in, so that we do tons of human factors and systems engineering, information architecture, habitat design, flight hardware, testing, development design, manufacturing, fabrication, assembly, all that good stuff, and an integration department, which includes our information architecture, collaborative human performance, and the group that runs NASA's human research program. So that's a lot. To talk a little bit about our TechNet, this is something that we started with this brand new contract. And with 40 or 50 years of experience in human spaceflight, there's a lot of stuff that we know. But we know that we don't know everything. And even though we've been in space, we've had a constant presence for over 25 years on ISS, and we have supported human spaceflight since the beginning of the Mercury program. There's still new stuff that we learn all the time. As an example, we knew during the space shuttle program that when, which had missions of 7 to 17 days, probably at the longest, we knew that some crew members said, hey, like my vision's changed a little bit, but it seemed to resolve when they came home. But once we started doing ISS increments, and we started flying people for 6 months and longer, we realized that some of the structural and functional changes of the crew members in their eyes, some of them resolved and some of them didn't. And that's where that SANS, or spaceflight neuroocular syndrome, spaceflight associated neuroocular syndrome, came. SANS, just called SANS. So, so we know that we don't know everything. And so with HHPC2, we built what we're calling a technical network, or the TechNet, which is a coalition of trusted and experienced industry and academic partners. We know that there are companies and universities who are doing world-class research, who have subject matter expertise, niche capabilities that that we can use to help NASA solve their problems. And so building and using this TechNet actually allows us to provide surge capabilities and skill sets to NASA, helps us do more advanced research than we're able to do on our own, and to touch base with subject matter expertise. The other thing that's certainly an issue with my job is we want to make sure that we build a really strong an internship program with our partners that develops a talent pipeline. And that's everything from undergraduate interns to postgraduate students. And I say that really based on my own experience. I started as an intern at NASA in 1993, thinking I was going to go to JSC. I was going to do my internship for 10 weeks, and I was going to say, thanks a lot. I was interested in public health. And 30 years later, I'm still here doing a career I never thought I could do in an industry that I absolutely love. So our academic partners on the TechNet are Texas A&M University and Louisiana State. And both of those universities have strong aerospace medicine programs. In order to be a NASA flight surgeon, you have to graduate from, you have to be a board certified aerospace medicine physician. And so those programs have those. Texas A&M is also the location of our food production facility for NASA. So that's where a lot of the food is made for the crew. The University of Houston in Clear Lake has a very strong human performance area. Ohio State, you guys have a huge engineering department, and of course hosts the Deep Space Food Challenge. So I'm super excited to start to talk to you guys about food. Embry-Riddle has a strong human factors program. Rice University has the Rice Space Institute and a very strong synthetic biology and wearable sensors program. And the Mayo Clinic, we have a long-standing partnership with them doing translational medicine. Our industry partners are a lot of small businesses that help us meet the small business goals that we're required to have on this contract. A lot of big government contracts have those requirements. But Anadarko, Geologics are both engineering firms that we have previous relationships with, and they have niche capabilities that we may have to tap into. Insight Global is a staffing firm. I don't know how they do it, but they have the ability to find, like, you need somebody who's got like some really weird skill set. They have the ability to find it. Oceaneering for precision robotics and safety, and then of course Intrinsics for IT and systems engineering. So We're in the process of working out our master service agreement with OSU and the other academic partners. What that does is that establishes all of the terms and conditions on our subcontract. And then every time we need some specialty, subject matter expertise, I'll probably give Jessica a call and say, hey, can you help me find this? And we'll get folks to help us out. And it could be for just a couple of hours of work, or it could be a couple of months of work, with the ability to utilize students and research and anyhow. So I'm super excited about this, and gonna work really hard to make this a success on HHPC2. And then I think I'm right up on the edge of my time. Our strategic initiatives, it's really hard to fit on one slide. But basically, what we're trying to do on HHPC is to make NASA's mission possible. So any way that we can enable exploration by leveraging NASA capabilities that creates value for us, of course, we're still a corporation, for NASA and the agency, but as well as for our industry and academic partners. So that's growing the LEO economy. That's something that NASA really, really wants to do, and we are committed to helping NASA do that, supporting lunar exploration, exploring adjacent industries that can benefit from human performance expertise that we have. We do a lot of stuff with, we've done stuff in the past with NASCAR, and the auto industry for landing loads and injury profiles on the crew when we decided that we were going to land on land. So that's sort of like an unusual, we have an annual, it's called Pumps and Pipes, where the aerospace industry, the Houston's oil and gas, and Houston's medical centers, those are the three big industries in Houston, get together to talk about what the commonalities and the crossovers, and that usually happens, I think, in December. So we really want to leverage this TechNet to help you guys, help us infuse technology and research. You guys have the ability to do this, anything that help. We're looking for anything that helps us do autonomous exploration. And I know we mentioned a little bit about ground analog. I didn't mention analogs, but we also run NASA's analogs for them, the Human Exploration Research analog, which is like a 45-day analog, which it's kind of like a capsule. It's more like a station. And then the CHAPEA analog, I don't know if you guys have heard that these are the 1-year analogs that we're doing, that are Mars-like missions. So yeah, so we're part of developing this, but we also know that a lot of our focus is on operations. And so we're hoping that our TechNet and our participation in groups like the Human Performance Collaborative can help us bring these top-notch and state-of-the-art technologies to NASA, so that we can fly people safely. That was a lot.
That was
That's my last
fantastic.
slide.
Thank you so much, Dr. Merkle. That was really, really fantastic. And gosh, I'm so excited to see all of the great partnerships that we will hopefully have moving forward, HPC, Starlab, OSU, and KBR. As I mentioned earlier in our chat, for our participants, we will have a 5-minute roughly Q&A period following each speaker, where you'll have the opportunity to ask directed questions to that specific speaker. Of course, if you have a question that comes up later during our session that you want to ask of a specific speaker, you can ask that during our more general Q&A panel at the end as well. But this is really an opportunity, while everything is still fresh in our minds, to dig into the presentations being provided. So with that said, if anyone has a question that they would like to ask Dr. Merkle, please feel free to, how best to do this? I guess raise your Zoom hand and we will unmute you at that point, and that way we'll avoid having people jump on top of each other. So feel free to just raise your Zoom hand if you have a question.
Or you can throw it in the chat and we'll monitor that as well.
Yes, that too. I will start out by asking a question while we give people a little bit of time to noodle over if they have any. Dr. Merkle, I know at the end of your presentation, which was fantastic, by the way, I'm absolutely blown away by how much KBR does across such a vast range of research and support areas. But at the end of your presentation, you had briefly touched on the work that KBR does in analog support for NASA. Can you tell us a little bit more about what the intentions and goals are behind both the CHIPEA and I believe it was the Human Research
Hera.
Analog?
Yeah,
Yeah.
Hera.
Hera. Perfect.
Excuse me. Yeah, so Hera is an analog. Looks a little bit like a two-story habitat. And traditionally, we have used that analog in 30 to 45-day increments. Usually we do campaigns that are typically 4 missions in a year, each lasting about 45 days. And very often the goal of those is probably twofold. One of them is, usually very often we do team dynamics in those during those missions. So very much looking at mission timelines, team dynamics, how are people getting along, putting different skill sets together, those kinds of things. And we have a ton of add-on research. So NASA will come up with, here's like the mission profile, and here's the goal of what NASA wants to accomplish on each one of these. And then very often they'll do a solicitation that will allow researchers to sort of do add-ons. So we can do, anything from biological samples to, psychological inventories, those kinds of things. CHIPEA is a new analog that we built probably 2 or 3 years ago. It was actually 3D printed because we think that that's the way that we will be getting a habitat established on the Loon or Martian landscape. We may or may not have SLS, which is our big heavy lift rocket, depending on what the administration does. We have commercial providers that are working on their own heavy lifts. But it was 3D printed. It has a Martian landscape. The crew does simulated EVAs. They are on that mission for a year, so they're locked in. There's that also twofold. Looking at again, a lot of team dynamics, sleep shifting, a lot of sleep studies. And the other thing that we do with CHIPEA is its main purpose is actually looking at a Martian food system. So the crew are consuming what we think may be the Martian food system when we go to Mars. So we also support the NBL. In the past, we've supported NEMO, which is the underwater analog off the coast of Florida. I don't know if anybody's doing NEMO anymore, but and then we've also done Hot and Mars, which is the Arctic crater. We've done work down in Antarctica. We've done research down there. So we're big on spaceflight analogs and looking to possibly establish one in Australia. So lots of, yeah. It's a big contract. It's 10 years. It's worth about $2 billion. It's a big contract, and it covers a lot.
Sounds like it covers honestly just about everything.
Just about.
Just about, yeah. Well, thank you so much for those additional details. I really appreciate it. As a reminder for all of our attendees as well, if you would like to connect further with anyone on our teams or any of our panelists at the end of these sessions, feel free to shoot us an email and we'd be happy to make sure that you are connected via email and such. That said, not seeing any additional questions popping up. Oh, it looks like Nicholas Tiley, would you like to ask a question of Dr. Merkle?
Yes, if that's all right. Can you hear me,
Yes,
Doctor?
absolutely.
Okay, I had a question for you. So I've been working with the HPC for a while as a partner, and I'm active duty Navy. And I was just curious, have you guys worked, with the Navy regarding aerospace operational physiologists, the maritime space officers, I'm just kind of thinking, I didn't see any like DoD sources related to your partners. Can you kind of dive into how the collaboration between the two have, been going on to counter those physiological abnormalities you mentioned?
Sure. So the one I'm thinking of specifically, couple of years ago, well, I guess maybe 10 years ago now, was when we noticed that there were these structural and functional changes in the eye that may or may not resolve after long duration flight. Um, One of the things that our scientists thought might be causing it are pockets of CO2. We actually did a long collaboration with the Navy, looking at similar issues with submariners. But so yeah, I didn't talk about specifically about some of our DoD contracts, but we do work with the Air Force, we work with the Navy. Um, a lot of our flight surgeons are military. Our optometrist is a former naval officer. So yeah, I didn't put all of our but yeah, certainly through the agency. The agency does those kinds of collaborations as well, reaching out to Space Force and DoD, and I work with their chief scientists to help establish those. So if there's somebody you think I should talk to, let me know.
Thank you.
Absolutely fantastic. All right. Thank you so much for that question and for the response, Dr. Merkle. I think it is time now to move on to our next speaker, which is Dr. Mason Robbins, the CEO of Starhelix. So, Dr. Robbins, please take the floor. We're excited to hear from you.
Thank you. Thank you so much for the invite. And I apologize if it cuts out, just like flag me and I'll go back over something. We're having a storm come through and it seems like and then it crashed and then it made me upload the new software. And it's like, oh, come on. But cool. No, thank you for the invite. Let me see if I can share here. So screen 2. We're going to share screen 2. Perfect. I think that's where we're at. So all right, Starhelix. So as you can tell by my accent, I live in Edinburgh, Scotland, but I'm originally from the States. And we are Scotland's first biotech space company focused on human spaceflight. So my background is in human factors engineering. So I like to, quote, protect the squishy bits in the system when we're dealing with humans in spaceflight. And yeah, so just going to have some fun with this and kind of show you where we're at in Scotland, go into kind of what the tech and testing we're doing, kind of look at how we look at astronauts, and especially in a part of the world that is thinking about getting more into human space flight, then how we use spacesuits as analogs, and then kind of our pipeline of tech and where we're at right now. So we might be one of those plunky little companies that KBR is interested for TechNet and some novel solutions or something like that. So kind of cool to be on the same panel here. But
Let's
as I
chat.
listed on the, yeah, definitely.
Let's chat.
So as I listed here, we're based in Edinburgh, Scotland, but we're also registered in the US. We are a virtual tenant of the Vista Science Park, and we are in the process of securing payload on Starlab right now as we speak too. So we've got this great connection going along. So without further ado, I'll advance the slides if my computer will play nice. I might have to do it manually. Here we go. Next slide. All right. So I had the privilege of, so Scotland's started getting into life sciences recently, and had the privilege of being on their first ever working group today, actually. And so just wanted to kind of share where we're at right now. So Space Scotland has put together the Scotland's life science group, really focusing on the biomanufacturing and microgravity, bio-derived materials, advanced biomedical monitoring, and how we can bring like this really great industry in Scotland on the biotech side, along with the space side. So on top of what we do with our own development, because we have this existing and growing relationships with like Voyager Technologies and some of the partners there at Ohio State, we're helping with some tech transfer of some bio companies and see there's new ways to get into the industry as well. So it's been this kind of fun voyage, this fun venture that we're getting into. But, Scotland is a country that is so innovative and so resourceful that, you know, we try to figure out the questions that people don't even think about before they think about them. So it's a cool time to be involved in space and new space. Just wanted to give a quick overview of it. The areas in green are actually where Starhelix focuses its efforts on. And a lot of that is around on the wearables and tech. We test in our test bed. We operate a full pressure suit, and we've got access to stuff that could even go up as high as 8 psi without losing dexterity and mobility and all that kind of stuff if we need to. And then we're looking at biomaterials, protective textiles, regenerative life support systems, kind of around bioreactors, microbial recycling, and some crazy stuff that you would read in probably red Mars, green Mars, blue Mars type stuff. But you know, you got to push it somewhere. At the end of the day, we're all dreamers, I guess. So, and we just love space. So that kind of gives you a background of where we're at over here. And what's crazy is when I started working and we formed this company, it was really Earth observation and small sats was the big thing over here. But just in the last 2 years, we're starting to see how other industries can get into space and what does that mean and what does a global space economy look like. So for us at Starhelix, we look at your traditional pathways of R&D, integration, demonstration, whether that's doing it ourselves, collaborating. We love to collaborate with across the industry now here, not just Starhelix, but the Scottish ecosystem as a whole is really great at collaborating because we're small and scrappy, but we always punch above our weight. But then for Starhelix, what we bring that's a little bit different, and we're trying to show that you can be a small, agile company, but with a large outreach, is that infrastructure and collaboration with parabolic flights, roadmaps to flight certification, and then analog sites. And when I got this subject matter for this talk tonight, analogs are kind of my bread and butter. I've done so much testing around the world in analogs, so I figured I'd bring some of that aspect into it, and especially when it comes to that extreme environment using biolabs and gravity simulators, whether it's the centrifuge or clinostat or something like that. And then we also have a relationship with about 10 universities across the US, the EU, and the UK that allows us to push some testing, but also kind of have this like give and take. I mean, the formation of where we were originally as a company is we were a bunch of PhDs who decided that we were kind of ready to get out of academia for a while, but we still wanted to have questions about what the world had to offer. And then suddenly it's become a company that we're feeling into different places all over the world. It's so much fun. But that brings me into the human in the loop approach to testing. And this is where my bread and butter baby is looking at astronauts as performance athletes. So suits as mobile test beds for emerging tech. The cool thing about a spacesuit, especially if you're designing something that's completely sealed and all that stuff, is it's a closed loop system. So you can really try different technologies. And we were working with some biosensors earlier this year that worked perfect in just wearing on your skin, but as soon as you put them under pressure and then you tried to move against that pressure, it just went all sorts of craziness. So that's why we see analogs as such a great opportunity. But I don't just mean facilities, I mean equipment to simulate the best we can for on Earth or in space or whatnot. Here's some of the campaigns that we've been working on, whether it's pre-breathe, post-breathe, exercises. I know KPR, I've had some friends go through your program that you've had, those campaigns with looking at different breathing and pressures. I'm involved with, at least I've passed the medical and the psychological for HERA and stuff like that. So who knows, I might end up at JSC sometime on one of those campaigns. But yeah, for us, it's just, again, looking at what kind of novel technology we can bring out there. And I'll get more into our specific tech that we're working on right now and some of those interesting ideas that we're trying to push. But we've found that sometimes when you talk to like engineers at JSC or you talk to Airbus or some of the big primes, you know, you've got things that you have to do and things that you have to deliver. So it's hard to push innovation. Same thing. If it's not broken, don't fix it. But it doesn't mean we can't challenge the understanding of how something's made or how something works. And that's where we try to be that agile little company that, like, all right, instead of ball bearings in your glove, why don't you think about moving different and how can you move in that? And then how can you 3D print it in situ? So when you're on the moon or Mars, and your part wears out or your hardware wears out, how can you replace that without having small parts that might get lost, or add mass, which is one of the greatest challenges when it comes to human spaceflight, is getting things out of the gravity well and up into space. So yeah. So, and then on that, when we're bored, we just try to test government standards and controlled environments to just make sure that, you know, this is what the baseline, can we achieve it, but can we be better than that, and see if we can still keep the same kind of results or even improve performance, but without an increased cost, to then write a white paper or something, say, hey, have you thought about doing this? Just because you've done it for 50 years, does that mean it's the way that we always should do it? So it works when you're a smaller company, but at the end of the day, you try not to kill yourself either. But no, we never do anything that puts people into harm. I think our review boards would kill us for that, but you still got to have fun doing it too. Cool. So spacesuits and wearables for analog settings. So these are a few suits that we've been working on, and environments we've been working in. So like I said, the Arctic, we were just, funny thing about Houghton Mars crater is there's two facilities, NASA's facilities and the Mars Society facility, and they're like a kilometer away from each other, but there's some cool opportunity there as well. So we got to take one of our pressurized suits up and run it around in the crater there in Arizona, out in Poland, Hawaii on the old lunar yards. We've done MBLs, which are always fun because you quickly find out when you're working with like an experimental aircraft, an experimental suit, you quickly find out as soon as the pressure's taken off that there's a leak suddenly in your boot you didn't realize. But you know, even the EMU suits on the ISS leak quite a bit too, but as long as you're putting the pressure through, you know, don't want to get too much into the craziness in there. But those are just kind of those nuances, those crazy things that you learn. And again, talking more towards the analog thing, we constantly get like, well, why do you do it? Or why, like, some are like staying at a hotel where other ones are in the middle of nowhere that takes hours or days to get to or whatnot. And, you know, each facility has its own pros and cons, how it's set up. But what we learn is not only do you have to rely on your team, but if equipment fails and you're in a closed system or you're far off in the middle of nowhere, you just have to improvise. And so, I mean, I was realizing during the call, I have a little valve thing that I had to rig up with some zip ties and all that, because I was in the middle of doing a test project up in the Arctic, out in the field with like the battery on the front of the ATV and a compressor on the back, and someone sliced my air tube while I was working and stuff like that. So it's how you slice it or splice into those kind of things and just work really quickly and just solve those issues. So whether you're in the middle of doing a test or study, and then one of those little things happen, it's just like being in the real world. I guess what helps for us is you can pop your helmet if you need to, if it's absolutely a catastrophic or life-threatening. So if we can figure those things out, but then also give protocols that, all right, this, or this has happened, here's some pointers or here's lessons that we've learned to mitigate that, then that will hopefully one day save someone's life when they're on the moon and they don't have that luxury of just popping the top or something like that. So that's why we see this as really valuable and kind of pushing where we can go. Current technologies. So this might be a little bit more of the interesting area and where we're at, and some of evolution from when we were last in Ohio. Our main one that's actually a TRL, it's being used in the dental industry and in the military, but we're bringing it into the space sector. It's called Remora, and it's a novel patented sustainable platform technology. Basically, it stops biofilm formation for 6 to 9 months with one application. And the cool thing about this is you add it to your existing cleaning protocols. And if you do the math for like the ISS, if you can reduce cleaning, if say one astronaut cleans for 3 hours a week, if you can reduce their cleaning to just 1 hour a week, you're saving NASA 50 million a year per astronaut type of thing. So when you're starting to save time like that, but the cool thing about it is you can polymerize it and you can put it into the water systems or whatnot. So you'll prevent microbial growth. You'll prevent those biofilms. And then what we're finding in Scotland up here is rocket companies are now interested in it in their water systems for rocket tests, because right now they're using chemicals, but they want to put the water back into the system after they're done. So it costs a lot to treat that and put it back. Well, this is a non-toxic substance that can basically prevent biofilm formation, algae, bacterial growth in your system, and then it won't hurt the environment. So it's a green technology that can just go right back into the system. So it also is used for contamination. We're running a study with Leicester University soon on clean rooms integration. So then this could be inside a spacesuit, this could be inside a space station, this could be in your water systems or something like that. So it's a cool technology. The next that we're working on again is biosuits, biospacesuits. So looking at origami and biomimicry to design better suits that then could be 3D printed. So we found as a small company, you can't say you're really a spacesuit company because the big companies are going to be like, we don't care, come at us, like we can do everything. But what we found is if we could work on components themselves, then components can feed into the supply chain. And yes, we can build an MBL suit for 50 grand type of thing, and it'll perform exactly like a legacy suit and whatnot. But the niche for that as a company is small, but if we can build components that then also have terrestrial applications, we can feed into a NASA legacy suit, but we could also feed into the defense industry or PPE or some of those kind of areas that could use the same technology. So we're finding as a company, you want to do all these grand things, but if you find those niches, you actually can find your little fun pick into there. And then the last couple of things I'll talk about that are in the pipeline is we've got a melanin-based radiation protection that is lower on the TRL, but it shows high promise for a broad spectrum of radiation protection. And when you're thinking about melanin, as opposed to water or iron, the mass of that is so small, and there's some chances that we're looking at synthetically producing it, but there is some chances that you could organically create it as well. But that's, again, none of us are biologists right now. So if there's any biologists who want to play with this, happy to collaborate or whatnot. And then the final one, and this is like your pie in the sky, like if we had unlimited resources and we have a partnership with the University of Edinburgh that they're working on that's going to need either time or cash injection, is biomining for critical minerals. But we've also found that you could do recycling with biomining. And if you can develop a way to basically recycle satellites in situ or on the moon or something like that, you can extract those critical minerals without losing them in the atmosphere or any kind of waste or anything like that. So then you have all of these essential critical minerals already in orbit that could just be harvested, brought to their elemental components, and then manufactured into whatever new component you need. So some cool ideas, some whatnot, but hopefully this provided a good overview of kind of a plunky little company from Scotland with kind of a global reach that just wants to have fun and make a difference and hopefully push us beyond where we are today. So yeah, that's me, and hopefully you learned some things about space in Scotland and whatnot. Thank you.
Thank you so much, Dr. Robbins, for joining us from across the big pond today and sharing the incredible work that Starhelix is doing. Much like with KBR, I think that we could have had you speak for an entire hour and I still would have had so many questions afterwards and such. So we'll definitely have to have you come back and give us a much longer presentation at some point, because the work that you guys are doing is just so incredible and has so many interesting applications and potential partnerships with it. That said, I think we have time for just one question from our audience. If anyone has a question, pop your hand up or toss your name or your question into the chat, and we will move that along. Oh, I saw a hand from Dr. Preeti Sawant. Okay. Please feel free to unmute and ask your question.
Hello, everyone. Thank you for this wonderful session and all the speakers. The presentations are really amazing. This question is not only for Mason, but rather all the speakers at the moment. I'm Dr. Preeti Sawant. I'm a general surgeon and a space health enthusiast. So my interests are in medical health technologies that can be applied in space health and reverse back to, global health perspectives. So anything on that part, I'd be interested to collaborate and learn more from the speakers and their, work areas. So happy to know about any leads on that. Thank you.
Oh, that's interesting. One comment that I would have on that I know that we're looking at over here is one of the spaceports is that would be like a recovery for like your dream catcher or dream chaser, kind of the horizontal landing. I was looking at space medicine and trying to develop, or sorry, space nursing. We're developing a lot of space doctors and all that, but what about like more of the nursing type care or something? So one of those that no one ever thought of it, so why not try it or something? So cool.
Awesome. Well, thank you so much for that question, Dr. Spot, and for the response, Dr. Robbins. Hopefully that'll be an ongoing conversation that maybe continues into a partnership in the future. Next, we are going to hear from Noor Haj Tamim, who is the CEO of Avionova, which is a very interesting company that produces and creates technology to improve the human experience, both on Earth and in space. But rather than hearing me prattle on any more about it, I will pass the microphone off to Noor and hear all about your experiences in space research and with Avionova. Thank you for joining us.
Thank you, Abby. It's great to see you again. I do have some presentation put together. Half of it is about Avionova itself, and then half of it is about IAS, our spaceflight organization. Let's see. So engineered for space, built for Earth. Myself, I'm a huge tech transfer fan, have been since the ripe old age of 7. I've always been just in awe of how, the memory foams in our mattresses were part of astronaut suits, or how NASA is the reason why we have EKG monitors and so forth. So it's really great to be able to have a tagline just like this. And it actually was a space technology earlier on. So the way I came across the technology that we're using for Avionova is a bit unorthodox. I'm a commercial astronaut candidate with the International Institute for Astronautical Sciences, based in Boulder, Colorado. And I had a parabolic flight assignment with Canadian Space Agency. I believe this was about 2 years ago, and my peers, they all had their own experiments and payloads and were working with organizations to actually carry out research. I had no idea that this was a thing. I, had that insane FOMO experience, like, oh my goodness, I need to find something. And at IAS, we have these textbooks, and essentially they're these massive manuals of how to go to space. And I find it humorous that we had checklists for the Virgin Galactic spacecraft that almost looked exactly like Cessna 172 checklist. So I'm scrolling through this big textbook and I'm trying to find something, and it just kept popping out to me, the space motion sickness problem, where 2 out of 3 people experience vestibular abnormalities going to space despite their training or despite how many times they've even been to space. 2 weeks later, I ended up developing my own vestibular disorder. And it's kind of funny because, well, first of all, just keeping up the signs. It's how do I say this? When I was looking into these textbooks, I kept thinking to myself, oh, that's so interesting. I've had these experiences before, but I've never been able to pinpoint it. I've had the room spinning, and my vitals been fine, but I don't know what it is. And I mean, this led me to go on a deep dive to learn that 40% of people around the world, not just Americans, experience vertigo, and that 6% of people worldwide, they lose their jobs because of vertigo. And actually, there's this very interesting cycle that patients essentially go through, patients like myself, where there's a period where you have this big spinning, scary sensation. You don't know what's going on. So you go straight to the emergency room. You try to explain to them your symptoms. And it's also really difficult to explain. Because again, I didn't know that I was having vertigo until I was reading through the textbooks and it was describing exactly what I had gone through. And you go to the doctors, they immediately want to rule out the big scary stuff. So they put you through CTs and MRI machines. And clearly, they want to rule out strokes and tumors. But often what happens, because the ears are so severely under-researched, is that patients, they're given back their clear head scan and they're sent back home on their way. So these patients, they're part of 60 billion annually recurring health cycle, one, because of these scans, two, because they start going to the forums. They try to figure out what's wrong with them. And they find that someone made a post about this amazing doctor that's trying this new antihistamine approach in Colorado. So they end up flying to Colorado to go try out this new method. And then, they might be fine for a couple of months, but essentially what ends up happening to them is they're going to have another episode because these are relatively unpredictable, and they end up back in the emergency room. So we're really here to stop that. I've already went through this. Existing medications, this also applies to astronauts as well, are drugs and surgery, or surgery not for astronauts, but surgery for people on the ground. And then these drugs include meclizine, Valium, so really just sedatives, nothing that really truly targets the ear just yet. Our core device uses bilateral cooling to help suppress vestibular activity within the ears. So our eyes and our ears control our sense of balance, and when the fluid in our ears starts to overact, that's when we get the symptoms of nausea, dizziness, disorientation. When people ask me about different applications, such as spaceflight or even cruising, I again like to tell people we all have the same ears. Unfortunately, the vestibular system, this unique part right here that controls all of our balance, cannot truly be trained. This is an example of our medical device. We have two different technologies at the moment. This one uses different levels of cooling and heating to elicit a baseline response within the ears, because generally when one ear starts to overact, the other tries to compensate, which adds a lot of stress to the body. And it also slows down the activity within the ear to help communicate with the eyes better. So eventually we're able to slow down that spinning effect. We're actually working with Ohio State University on this. I saw Michael DeVerso in the call with us. Working with Dr. Shu, we recently submitted an NSF grant to continue development of our medical device. We also have a different application here, primarily for cruising and seasickness, as it is a derivative of complications from the ears. And that device is going to be in trials, I believe, in May with two different customers, which are Uncruise and Polar Expeditions. So I have a couple trips to Antarctica coming up, and fortunately I can say it's for research. I'm gonna be so cold. I was raised in the Middle East. We are super lucky to have a space flight with Halo, if you'd even call it a space flight. It's a stratospheric balloon company operating out of Saudi Arabia. And what they're finding is that their test trials, the spacecraft itself is starting to spin. So they have somewhat of a dizziness issue that they are anticipating that their passengers are going to have. We are going to be doing the first ever vestibular testing in a commercial stratospheric balloon. And essentially what this means is the first time we're going to be sending up the pilot himself of the spacecraft to end up wearing these big goggles that track your eye movement, so we can figure out when exactly the spinning is starting to happen to these people and how to best mitigate against that. This also helps us determine if our device for medical is more applicable to something like this, because again, it's a 4 to 5 hour space flight versus something that could be maybe 20 to 30 minutes long. So something that our seasickness earbuds could be used for. And I believe this flight should be happening in late 2026, early 2027. To talk a little bit more about IAS, it is a phenomenal platform for industry and students. Myself, I started going through this program when I was 17, gained, first of all, lifelong friends, second, it's just an incredible group, and I would say testing basically at your fingertips. So being someone who's tried to go through the government system, it takes a very, very long time to get technology out there to the test beds. So I was working on a modulated de-icing technology for fixed wing aircraft back in 2021 with a group. And I mean, this was during the pandemic, but we were contacting NASA Glenn for their icing tunnel in Cleveland. And I actually didn't get a call back until I think 2 years later when we were, ship has sailed. So at least, IAS were able to maintain that direct communication. And IAS uses different international test beds to help companies get their payload results quicker and at a cheaper rate too. And that's part of where the parabolic space flight was coming from with Canadian Space Agency. Most recently, they had their IAS-01 flight with Kelly Girardi aboard the Virgin Galactic spacecraft, and they have a second space flight aboard Virgin Galactic's new Delta Diary series happening, I believe, next July, if I'm not mistaken. For this, they had 62 proposals coming in from all over the world for studies, all the way from stuff to be on racks to biosensors, and even a new spacesuit that's being tried on by Kelly and Nora. And then they are also working actively with Virgin Galactic to coordinate more space flights for more researchers to submit more payloads. I believe for this specific flight, they are taking up 25 payloads. And then they did the biomonitoring. They took the first, the diabetic tracker. I'm forgetting the word off the top of my head. I'm a little sleep deprived. And trying to think of what else. But they took a lot of really cool science and they've been presenting it and have some new findings as well, and so forth. Some payloads that IAS is able to offer are the neutral buoyancy testing, the parabolic flight testing, IVA suit testing. I actually helped make the connection for Halo Space to use their IVA suits because they are certified. And the big blue suit, or the orange suit right here, is actually going to be used on Halo space flights at a significantly discounted rate, as if compared to being able to use a university's spacesuit itself. And then I believe they also do Antarctic missions as well. To talk more about Avionova, founder and CEO, I'm currently a solo founder. I've taught at Oxford's Academy of Excellence for tech commercialization and tech transfer. I've done some programs on and off with NASA, again, for tech transfer. I just keep finding myself here. And did my undergrad in mechanical engineering, and I'm currently pursuing a master's in biomedical engineering, so still a student. Again, we're working with Dr. Shu with Ohio State to carry out our clinical protocols, and we have Alan Gilbert, who I met with from Techstars, which is a startup accelerator here at Ohio State. They have a program. They also take in space startups, medtech startups. It's pretty ambiguous in their cohorts, their pools, and he's an expert in tech commercialization. So we have, I believe, over 12 commitments from defense, space, and healthcare systems. Halo Space and IAS I'd originally mentioned. NASTAR Center is I believe it's the FAA's only private accredited testing and facility for people who are either military pilots themselves or are going to space. For example, if Blue Origin or Virgin Galactic decides to send someone up to space, they generally tend to send their candidates there or their passengers there. Working with Ohio State again, Vanderbilt University Medical Center, they're going to be testing our technology with their patients. And then we also just recently joined the Vestibular Disorder Association's Industry Advisory Council as well. And then again, to talk a little bit more about the motion sickness segments, getting hardware out there is really hard. So especially when it's medtech and you're still trying to find your ideal market, because we're still here trying to determine, is this preventative or is this active usage? And I mean, through that process, we were going around and trying to find, okay, well, if we made a smaller version that isn't as strong as a med device, what can we do instead to at least start building revenue by next year? Because we're a relatively young company. And, we'd spoken to Tesla and Joby, and we had interest from all over, but it was more of a, yeah, we're interested, keep us in the loop, until we started learning more about expedition cruising. And for the first time ever, we sponsored this conference in London primarily for expedition cruising. They announced our company. People started giggling to themselves, sharing seasickness stories, and we had companies and decision makers running to our table asking how to put our technology on their boats. And that's when it hit me. It was like, we hit our market. We know we're taking care of med tech in the future, and we're actively working on that. But this is a problem that we can actively solve, or even space in the future too. So far, again, we have our 2 devices, 12 letters of intent. We fundraised around like 350,000. Majority of it is non-dilutive funding from state-based programs. We have those 4 upcoming programs through the medical centers as well as the cruise lines, and that 1 space flight coming up with Halo Space. And then, yeah, for the next year for us, we're continuing to build out our med device and our seasickness device, figuring out how to make it more comfortable for the ears, and working closely with Ohio State University to ensure a good pathway to put these into patients' ears. And that's pretty much it. I know it's all over the place, but does anyone have any questions?
Noor, thank you so much for your presentation and sharing with us about your experiences with IAS as well as Avionova. I will certainly be keeping an eye out for all of your exciting upcoming work in the future. I believe we do have time for 1 quick question from our audience. So if anyone would like to ask Noor a question, please feel free to raise your Zoom hand or drop your name in the chat, and we will proceed as needed. Okay, I'm not seeing any questions, but we will be sharing for everyone registered here all of the slides and a recording of the event today afterwards. And we will also be posting our panelists' contact emails on our website after the event. So if anyone does have a question they would like to ask Noor, Dr. Robbins, Dr. Merkle, or Dr. Chiordi afterwards, please feel free to reach out to them. With that said, we are going to move on to our 4th and final speaker, Dr. Yasmina Chiordi, who is a professor here at OSU in the Department of Electrical and Computer Engineering and is also the lead of the Wearable and Implantable Technologies Lab Group. Dr. Chiordi, thank you so much for joining us today. We're excited to hear from you.
Yeah, thanks so much for the invitation. Let me go ahead and share my screen. Let's see. Okay. All right. Okay, so yeah, I'm Yasmina Chiordi. I'm an associate professor in electrical and computer engineering at Ohio State. I'll talk a bit about our lab, what we do, what I'm a part of, and then our research that relates to space, which has been ongoing for the past 5 years or so. I'm a member of the Electro Science Lab. It's a lab which is affiliated with the College of Engineering, and we have our own faculty. We're with the Electrical and Computer Engineering Department, but our research labs are at ESL. Our groups, our main office is there. It's 2 miles west of the main campus. 17 faculty, I'm one of them. $10 million in research expenditures per year. Great output, research output. And it's a very well-known lab, not just in the United States, but across the world, really, in terms of doing electromagnetic research, meaning wireless research, anything from a few hertz to optics and terahertz. So here's an extensive list of everything that's going on at ESL. I'm not going to go through that, but just from a high-level perspective, anything from like radar, photonics, remote sensing, radiometry of the Earth, and bioelectromagnetics, so biomedical applications, which is what my group is doing. So we call our group Wearable and Implantable Technologies Group, and we're developing hardware. And we heard from the previous speaker how hard it is to launch new hardware, and that's what we do. Our background is electromagnetics. We're working very closely with clinicians to understand medical needs, and we're developing new sensors. So we're at a low level, hardware level, trying to develop new devices that serve unmet needs. I would say primarily our work is on wearables, probably like 90% at this point, but we do have some work on implants as well. So the approach we have, it's for every single device follows this flow chart here. We're engineers, we do not know the clinical needs. So as a first step, we would interact with clinicians to try and understand what they need. And I'll say it's very exciting being part of Ohio State. We have access to all sorts of expertise from a clinical perspective, and our faculty or clinicians here are very much research oriented. So as opposed to a lot of what I've heard where they say, well, clinicians have their own practices, their own kind of technology, they're not interested in new stuff. That's not what I'm seeing. Every time I talk to them, they are full of ideas on what we could potentially offer to them. So I haven't identified a clinical need. We proceed with theory, meaning coming up with an idea, see if that works on paper. And if it does, we start with simulations, meaning we have models of the human body, anatomical models. It could be like male versus female, it could be kids, very high resolution, mimicking all types of organs and tissues. And if that idea works in simulation, we proceed with fabrication and testing. And for us, testing starts with phantoms. That means materials that mimic tissues. It's an electromagnetics problem, so it's not as easy as mimicking the shape or mimicking the mechanical properties. We're speaking about electromagnetic properties, and that has to do with how the tissues conduct electricity. It's a cooking process, really. As the simplest possible phantom would have water. Our tissues are water-based, salt, there's salt in our tissues, and sugar. But then it's a more complicated problem. Different tissues have different properties. So skin, you see here in the picture, versus bone for the brain, versus gray and white matter would have different properties. And those properties, to make it even worse, change with frequency. So even the process of making the phantom itself is not only time consuming, but also requires sometimes new science and new thinking. So once we have our prototype working on a phantom, then we'd proceed with testing. And depending on the complexity of the problem, implant versus wearable, we might start with animal validation, proceed with human subjects, or just directly skip to human subject validation. So all of our technologies right now might be at a simulation stage, others might be at a phantom stage, others might be testing with human subjects. So just to kind of sum up a high-level overview of what we do, it's interdisciplinary work. Our core expertise, my students' expertise, is bioelectromagnetics, so electromagnetics and how they apply on the human body, and to have extensive collaborations on signal processing, materials, AI over the past couple of years, I would say, and also, of course, our clinical inputs. So all I present is definitely due to my team, and I'll feature two of my students today. So we're here to speak about medical technology in space. And for us, for our group, that has happened through two of my students, Ali Rice and Sam Kugel, both of whom won fellowships through NASA. And that's the NST-GRO program. Ali just graduated, actually, so she completed her PhD with NASA support. And Sam is starting his second year now, again in the PhD program. And with the help of these students, we're exploring three main areas as of now. Again, developing new technologies from a hardware perspective and wearables. Bone loss, muscle atrophy, and muscle volume and function. Ali worked on the top two, and then Sam overlapped, got inspired by this work, especially in muscle atrophy, and built on to explore volume and function of the muscles. So in my next few slides, I'll show you a brief overview of each of these technologies and where we stand. So motivation, how it all started for us. We're monitoring the human body, and we read literature seeing that the musculoskeletal system is significantly impacted by microgravity. Bone loss happens due to the unloading, the skeletal unloading, but also muscle atrophy. There are exercise programs, we heard quite a bit about that, which are quite critical before the flight, during training, during the flight, but also when astronauts come back to Earth. And the idea is especially kind of thinking about long-term missions, thinking ahead. That's kind of a benefit to have in a research lab setting, the ability to think kind of not necessarily bigger, but the flexibility to resolve problems that might occur, I don't know, 10, 20 years down the road. So with that, we looked into technologies as of now and to identify several limitations in the sense that technologies exist for imaging, but they're either bulky, that could be like CAT scans or MRI technologies. There could be some portable technologies like DEXA scans. They still have ionizing radiation, so not something that you can use very often. And thinking kind of about the big picture where you have a long-term mission in space, where ideally you don't have clinicians with you, maybe you don't even have contact or communication with Earth. Can you have sensors that can be wearable? And when I say wearable, ideally seamless, maybe that be integrated in fabrics or just being extremely lightweight and very small, that can monitor these aspects as needed, when needed, at low cost. And kind of the last point for us, yes, this is kind of space oriented, but we would ideally want such technologies to be able to serve another purpose on Earth for civilians. Speaking of bone loss, you can think of elderly and how they may suffer from bone loss due to age, and that would have nothing to do with space. So yeah, the inspiration comes from space, but we're looking into kind of all sorts of applications that could benefit from monitoring, continuous monitoring of bone loss, muscle atrophy, and muscle function. So with that, my next 3 slides. Let me see. Okay, that's a question for me. All right, my next 3 slides will talk about each of these technologies, bone loss, muscle atrophy, and muscle volume and function. So bone loss. We developed, the idea here is that you have bone, you're seeing here a cross-section of the arm, and as you lose bone, basically the bone itself becomes more porous. I talked earlier about building phantoms, and I said we need to kind of mix water and salt and sugar to find the properties of the tissue. So in this case, if the bone starts losing mass, critical mass, then those properties will change. So that was the idea for us. We see bone as, let's say, bone without any issues, and then bone that starts being porous. And we treat these as 2 different tissues. And the question is, can we see these differences from outside? So the technology we built was applying 2 antennas. You see here number 1, number 2. These are wearable, so they're sitting on the wrist. The wrist being selected due to proximity of bone to the technology that we have around it. And what it did is we sent energy from antenna 1 to antenna 2. So you send power and then you receive power. And the question is, can I monitor the power I receive as an indicator of what's happening in between my wireless devices? And so we optimized everything. We optimized the antenna design, the operating frequency, the bandwidth, and so on. And we monitored this exact parameter, what I receive versus what I transmit. In the electromagnetics world, that's a metric called S21, and we monitor the magnitude and phase of that. And as you can see, there are big changes, especially when it comes to phase, 30 degrees for both female and male wrist. And that's between the cases of having an osteoporotic versus non-osteoporotic bone. These measurements have taken place in phantoms. So it's one of the technologies that as of now is seen at the phantom validation stage. So we had beef mimicking our average tissues, It would have bone and then beef on the other side, the two antennas placed on top and at the bottom, monitoring these S2-1 parameters. Moving on to muscle atrophy, the idea is relatively similar in the sense that we again have two devices, number one and number two. One of them transmits energy, one of them receives energy, and what we monitor once again is what we receive compared to what we send. So once again, you see the same S2-1 metric. And again, you're seeing big differences here, 45 degrees for one of our first sensor prototypes, 9 dB change in magnitude, and that's dynamic range. So going from the smallest possible to the largest possible cuff size in this case. This is a sensor that deforms with the circumference, basically, or the size of the muscle. So there has been quite a bit of thinking and materials development on how you build that stretchable sensor. We have two prototypes at the moment. One uses conductive threads. That's what you see here. It's a zigzag pattern. So the pattern of the thread changes as you stretch it. And the other idea was a liquid metal sensor, where in that case you have a tube with liquid metal inside. And so the dimension of that tube changes as you stretch it, and liquid metal just kind of flies around it. So quite a bit of improvement with the liquid metal. You see 80 degrees versus 40 degrees or 45 degrees of change, 15 dB in magnitude versus 9. But both ideas work, and I would say there are pros and cons. It's not just a better performance, it's a matter also of robustness and ease of wearability and so on. And this is a technology that, again, as of now, stands at the phantom validation stage. You see the visual here, but we have not yet tested on human subjects. And then the last technology, which got inspired from muscle atrophy, is the idea of kind of advancing muscle atrophy monitoring to seeing a more detailed picture or image of muscle shape or volume. So in that case, we have straps. So these are sensors, identical sensors. You can place as many as you wish, really, across your limb. And these sensors will derive circumference at millimeter level resolution. So let's say we have these three sensors here. They could give me a picture of the muscle like this. So 3 measurements of circumference, 3 independent measurements of circumference. So that's one aspect, volume. Like I said, at millimeter level resolution, there is again a sensor that stretches, but in this case, the operating principle is different. You have one standalone sensor, and you don't need the idea of 1 versus 2 antennas and transmission and so on. It's a standalone strap that operates by itself. And then some very recent findings. We got them actually this past summer. My student went to JSC and collected measurements on human subjects in this case, where we monitored power from the sensor versus torque. And that was through a gold standard dynamometer. And we see correlations. We have 20 subjects at this point, all of the measurements validating this relationship. So we're trying to advance technology to not just circumference and volume, but also quantification of function, thinking about exercise science, physical therapy, and so on. And like I said, yeah, this is one of the technologies that are at the human subject testing stage right now. And just kind of to wrap it up, I talked about technologies that I'm working on in collaboration with NASA for the student fellowships. But in my lab, we have other technologies as well, may that be through NSF funding or NIH funding, and we do see potential in them being applied to space applications, which is something we want to pursue or we're thinking about pursuing. One is motion capture, so we have smart clothing that monitors joint angles. We have technologies that monitor magnetic fields of the body. So our body transmits magnetic fields, our heart transmits magnetic fields. We're building wearables to monitor such fields. That could be for cardiac health. It also ties to brain health and cognitive load, which can be important in such missions. And we're also developing technologies for imaging, microwave imaging, that could be, again, portable and non-ionizing. So with that, I'll pause here. Thanks again for inviting me, and I'm very happy to take questions.
Amazing. Thank you so much, Dr. Chiordi, for joining us and sharing some of the really interesting work that your lab is conducting in this field. Rather than have individual questions for Dr. Chiordi, I think that we will jump right into the overall Q&A period for our entire panel. I believe that Noor has had to depart, but we have Dr. Merkle, Dr. Robbins, and Dr. Chiordi here to share their considerable experience in space research with us. And of course, you can still ask a question directed just at Dr. Chiordi or at any of our other panelists, or more generalized ones. I will go ahead and ask a question to kick us off while people noodle and ponder on some of the things they'd like to hear about. But once again, if you do have a question, you can either drop it in the chat or you can raise your hand and ask in person. So my first question is actually directly for Dr. Chiordi, and I'm curious to hear, what advice do you have for academic researchers who are not involved in space research yet, but are really interested in breaking into this field?
And so I was one of those researchers. Honestly, I didn't know that NASA would cover the type of research that I am doing. So I've always been doing bioelectromagnetics research. So I talk about NSF and NIH. But in my mind, when I thought of space, I thought shuttles and electronic devices. And I didn't realize about the needs that they have in this field. And then I realized the resources they have online. So my starting point was really websites and kind of literature review and to kind of understand what's out there. And from that point on, it was easy to get in that space. I work with students, so my kind of access to those resources was through students. But I would say kind of exploring the depth and breadth of their needs is critical. And one thing that I had to learn in engineering, and the hard way, and my students are learning it, sometimes the hard way, sometimes I have to say that, is that again, we're engineers, we don't know what the needs are. So for me, it took some time to understand what they are looking for and see how we can get there. And they're always very willing to kind of talk about their needs, explore research directions. So yeah, just kind of learn about them and what they're looking for.
Fantastic. Thank you so much for that advice. And I'll just put in a plug here as well for our friends at HPC, that when it comes to doing any sort of needs analysis or looking at the needs for potential projects that have to do with human performance, bioastronautics, anything like that, they are fantastic partners and collaborators to bring into those questions early on and can help to dig out some of those details. So I see a couple of questions in the audience as well, which I'm excited to hear from. So our first one will be Yara Fisher.
Yeah, thank you. This was very interesting. I am an associate professor and vice chair of research for physical medicine and rehab department. It's a clinical department, and I'm a translational scientist. And the human model that we studied for years and years is spinal cord injury. And funny that I did my dissertation on whole body vibration, being inspired by the NASA model of Dr. Rubin's Turkey model of vibration, bone, and muscle loss. So I did my postdoc in muscle biology and nutrition and microbiome. I'm a very diverse trained scientist, and I was telling my lab recently that actually now we can reverse the model and then apply what we learned from microbiome and muscle science in spinal cord injury, which is an anti-gravity model. There are different things in metabolism and autonomic nervous system, but it's very applicable in terms of what can we do with astronauts. And now listening Dr. Corti, the sensors for muscle loss, we do a lot of muscle biology with anti-gravity and also electrical stimulation and microbiome research for muscle loss. We're actually targeting bacteria that can be supplemented for perhaps spaceflight, or we're focusing on spinal cord injury that will decrease the muscle loss. All to say that I really don't know how to be involved with you guys. Perhaps you can show me some potential ways, either individual meetings or meetings like this, like a Shark Tank type of idea meetings, and I'm happy to just kind of be involved with it.
Just very briefly, we need people like you. So on my end, I need people like you. I mentioned earlier, we don't know what the applications are. We have a sensor that can monitor circumference at millimeter level resolution. So I really want to talk to people and say, I was actually thinking of hosting a couple of workshops and have people like you and say, why would you need that? And how can I refine it to meet those needs even better? May that be materials or resolution, footprint, and so on. So there's a lot of room for changes. This is not a one-time solution. So yeah, I'll reach out on my end. And yeah, I'm always happy to listen to kind of new application areas.
Fantastic. That is exactly what we want to see from these workshops, is those types of connections being made and hopefully more great space research being born. So thank you both for that. Now I see Dr. Jeff Rouse has a question. So go ahead, Jeff.
Hi, thank you very much. And thank you to all the presenters for just an awesome presentation. I learned so much. So very, very cool. And also thank you, Dr. Yara Fisher, for literally setting up my question. So just a touch of background. I'm a medical doctor at Tulane University, but I'm also chief medical officer of a company that has actually partnered with Dr. Hagen. Hi, Jessica, because we've gotten a couple of phase 2 grants with the Air Force and soon to be SOCOM, using Ohio State as a research partner. So my overall question is for all panelists. Oh, and Dr. Yara, our stuff uses whole body vibration. So thanks for the setup. So my direct question is this. So the pathway for industry to collaborate in the Department of Defense is very clear. There's lots of pathways, there's lots of SBIRs, STTRs, yet the pathway into the space world in NASA world is a bit more opaque. And we've learned about de-risking grants for existing health and help human performance technology that's good on Earth to potentially transfer to space. Quite funny, actually, the CEO of Starlab is literally a customer of ours, so I've had the opportunity to go to Starlab a couple of times and demonstrate our technology. But my direct question is, what are the sort of first doors for industry who might be looking for both research partners as well as programs within the spaceflight federal government opportunities? Thank you.
So I'll take a stab at this. I put a link in the chat. JSC has what they call their front door. And in there, you'll see links to the capabilities that we have at Johnson Space Center, the competitive opportunities, ways to partner with the Space Center. Very often, certainly with the Human Health and Performance Directorate, which is the directorate that our company works with at NASA. If you contact them, they're going to tell you to call KBR. So really we tend to be the front door. Because of our collaborative relationship with NASA and being the prime contractor for crew health, very often what they have done is they've charged us with the mission of going out through our TechNet to find where are the new technologies, what are universities doing. We have the ability to if you guys have something that NASA is super interested in, we have the ability to help do technology demonstrations on orbit. We can help you manifest and fly a particular payload if NASA's interested in that. So so I'd say like the front door is probably the way to go. I will say that NASA, or certainly JSC, I won't speak about the agency, I'll speak about my center. We certainly understand that NASA can be a little bit more complicated to navigate. I recognize that. So yeah, I mean, really coming through KBR, I mean, that's part of our job is to help do these things for the center. So if you're having no luck at the JSC front door, you're welcome to come come knock on ours. I will tell you that KBR also, this is a pretty neat thing. We have a reimbursable Space Act agreement with the agency, and what that allows us to do is, I'll give you an example. If there's, it allows us to use NASA facilities, NASA capabilities. So the analogs, their laboratories, our acoustics and lighting facilities, to you can essentially buy them. You, like the community, can buy those facilities by the hour, and you can do that through us. We can run, if you wanted, if the facility is available and somebody wanted to run a 5-day mission in the Hera facility. We've done that for private astronaut companies like Axiom, where they've, in training their first-time crew to go up into space. We put them in our analog for 5 days, ran them through the paces, gave them some alarms and whatnot. And so you have access to some of NASA's expertise and their facilities through KBR. So, if there's things that you guys are interested in doing, things that you want to try out, or, potentially looking for a contact, feel free to give me a call.
Awesome. Okay, do we have any more questions from the audience? If not, I will ask another question, and then we'll probably have time for at least 1 or 2 more audience questions before we wrap up. We will be finishing right at 3, by the way, just an FYI that I respect all of your time here, and we will release you promptly. Although I would love to keep everyone here and chat about this for days on end. So my question for each of our panelists is I'm going to ask you to pull out your crystal balls and look into the future and provide what you think is going to be the next big challenge that we can help to solve in terms of astronaut health and astronaut performance. If you had to, I guess, pick one upcoming challenge that you think we'll face in the next decade that we could be thinking about now, what would that be?
I could give you a laundry list.
That's why I had to say if you had to pick one, because otherwise we're never going to end this
Oh.
workshop.
I'll give you 2.
Okay.
I'll give you 2. Anything, any sensor technology or whatnot that allows the crew to be autonomous. So think in terms, so certainly for my contract, it's medical care is certainly one of the big things. Like I mentioned earlier, we won't have the ability to return crew. So, one of the things that I know that we're looking at now is, like, what is the role of AI in helping crew members do diagnostics and treatment plans? How do we manage medical capabilities or medical consumables on orbit for long duration 3-year missions, right? So I think if you're thinking about things that are dealing with autonomy, medical care, allowing the crew to be able to deal with things when they're on Mars, there's a 20-minute there's a 20-minute communication delay. And if you guys have ever been in an emergency situation, man, 20 minutes is a long time for us to even get the question. And it's another 20 minutes before the answer goes back, right? So think in terms of autonomy. The other thing is a stable food system. And that's actually one of the reasons why we wanted to talk with Ohio State in the first place, because of the Deep Space Food Challenge. Having a shelf-stable, palatable food system for a crew that can last 3 years is super, super important for us. One of the things that NASA probably doesn't talk about enough is how important mealtime is for the crew. Their current ISS menu is on a rotation of about 2 weeks. So if you guys think about buying the same groceries for every 2 weeks for the next 3 years, you're gonna get real sick of. Could be your favorite thing in the world, but you're gonna get sick of it. So shelf stable, low mass. small food systems that don't require, hot water or refrigeration. Those I'd say are two big things that we will need to very successfully explore the moon and Mars for long durations of time.
Absolutely. That's so interesting. And I'm really glad that you brought up as well how important it is to think about the palatability of food and not recycling the same food types too often, because as we look towards this future where we are hopefully spending more time in space and going farther than we ever have before, the psychological components of that require us to think of the full human experience and the full system of how we can best support our astronauts to be happy, healthy, and productive. So that's really great to hear. For anyone who's interested, I would highly recommend looking up the Deep Space Food Challenge that Dr. Merkle has mentioned a couple of times that we hosted here at OSU. Just give it a little Google and you'll be able to find all the details about it. It was a really, really fantastic program that had some incredible technological developments that came out of it and that are continuing to progress to this day. So look that up. Also shoot me an email if you want to talk further about that, because much like Dr. Merkle, I am very passionate about sustainable food systems in space and would be happy to have that conversation at a later date. Dr. Robbins, I see that you're unmuted. Would you like to also take out your crystal ball and take a gander at this?
Yeah, I think for me and for us, it's looking at how do we get our astronauts ready to go whenever they get to the moon or Mars or wherever they're at. So whether that's forward contamination, like with the antimicrobial work we're doing, or if that's looking at how do you make a better spacesuit or a better spacecraft that can protect on radiation, or I'm really fascinated with the hand and the damage that spacesuit gloves do under pressure with the hands. So how do you improve existing technologies so it's even less impactful and you have less of the nails wearing off? Because if you're too broken down to operate after a flight to Mars, you're not going to be able to work 24 hours a week or whatever the current trajectory is in EVAs to build a habitat to survive or live. So it's trying to solve some of those challenges now. So when we're ready for radiation protection on longer duration space missions, people aren't radiating out before they even get halfway there. So
absolutely. It's a marathon, not a sprint, right? And we need to be thinking ahead in that way. Fantastic. Thank you. Dr. Chiordi, what do you see as the future of challenges that we need to be considering over this next decade?
Yeah. So you got me thinking when you asked the question. And at first I thought about kind of immediate challenges, and I was thinking from a technology perspective, imaging is very hard to accomplish. I know they have ultrasound now, but if we think about advanced imaging technologies like replacement of CAT scans, MRI scans, it is very difficult to develop from a technology perspective. So there has been research going on for decades. We're not there yet. So hopefully one day. But trying to think a bit more futuristic, my mind went to therapeutics. So kind of Dr. Merkle also kind of referred to that. It's not about diagnosing, but if something happens, what do you do? We have been working a little bit in my group on some kind of futuristic thing that might apply to space one day, which is the ability to do surgery in a minimally invasive way and 3D print devices through like a keyhole entry, really. So that's something that got inspired originally by space applications. Now we're exploring on the side. But I think kind of the idea is to be able to think big. Like, yeah, in this example I'm mentioning, the idea is you want to have an implant that be a pacemaker, and you don't have like an actual surgery the way we have it now. Can you have like a small hole that you open on the body, have a 3D printer go in and print your device on the spot? So again, you would not need a clinician, it's automated. You wouldn't need AI to figure out location, position, personalizing shapes. But I think, yeah, for kind of the long term, we need to think big.
Absolutely. Yeah, that's really interesting to think about. And that actually brings up another question I'd love to pose to the entire panel, which is, as you conduct research in the unique environment of space, how do you ensure, or how do you balance the creation of Earth-based applications for your work as well? Is that something that you take into consideration? Are you focusing solely on space research, or are you continuously looking for ways that you can utilize the technologies and processes that you're developing here on Earth for a much larger population?
I guess to start off, I'm a huge proponent of solve for space, solve for Earth, and vice versa. So it's everything that we try to do, and my approach and my philosophy is what solution on Earth are we trying to solve, but that space might give us that opportunity, or flip it the other way. So all these different approaches that, all right, if it's pharmaceuticals, the crystals grow in every direction. So actually, if you can grow something up there, then what's the Earth application? But in the same sense as if we're needing to throw it in a centrifuge to increase the gravity or something like that. So always trying to consider both sides of that puzzle or that equation to see where you can find the most benefit. I mean, we really like to look at space as not like a place we work, but just an application to what we do. So when you start thinking of space as an application, it's less of a, oh man, you work in space, you must be an astronaut or something, but more like, no, I mean, we're just space janitors and plumbers. We're just working in space or something like that. But in that sense, joking aside, is when it's an application, then it's like, all right, these are the limitations to this extreme environment. But at the end of the day, the end goal is X product that will benefit all humanity, type of thing.
For us, I'm thinking it's a lot about how you operate your lab, your research lab, and your academic environment here at Ohio State. So a lot of it is grant driven, and for us, it's hardware development. So when everything starts as an idea, it's basic science for us. Does it even work? And we have to be application agnostic. So that kind of NSF type of funding is application agnostic. Like we would bring up space applications as a potential kind of end goal, but it shouldn't be just that. And then, yeah, we have students who are now working towards kind of space applications. But again, on my end, as their advisor, I have to think as big as I can. So I'm trying, even though I very much enjoy space applications, I'm trying to think beyond that. Yeah, like NIH is something I definitely always have in mind. I mentioned about how like kind of bone loss is equivalent monitoring osteoporotic bone for us. So the technology can apply to non-space applications. Granted that we have to optimize our sensors, refine them, both from a hardware perspective, an algorithmic perspective, maybe even materials and looks of the sensors for different applications.
Fantastic. Thank you both so much. I have to admit that I was biased in asking that question because I also hold a solve for space, solve for Earth mentality, and was hoping to hear that from all of you as well. So I'm chuffed. But no, it was really great to hear that perspective, both from an academic and an industry direction of how that involves itself in your decision making and research processes. So thank you both. I do think we are just about at the end of our time now today. I'm so grateful and thankful for all of our panelists. Thank you for joining us today, and so grateful as well to all of our participants who have joined in and helped create this fantastic conversation. I'm hoping that the conversation won't stop here. We have another session coming up on December 12th that I would like to invite everyone here, and please feel free to share that invitation widely with anyone who you think, any of your colleagues or friends who you think may be interested. They don't need to be space researchers yet. We're hoping to make space researchers out of all of you. So please share it widely. You can find that invitation on the HPC website that was shared in the chat, and we'll make sure that that goes out to all of you in an email as well. The December 12th session is again from 1 to 3 p.m. over Zoom, and the topic for that one will be microbiology, immunology, and human health in space. We will once again be intersecting academic and industry professionals for a panel and discussion, as we did today, and I hope to see a lot of you there. Before we wrap up, I do want to give a special shout out and thank you as well to our organizing team, Jessica Buskirk, who is here with us, as well as Sam Shattuck, also from HPC, who was not able to join us today as he had another commitment that he was attending to. But this workshop series would not be possible without the really, really incredible work that they have been doing on it. So I appreciate that. And to wrap up, I will just say once more, thank you to everyone. Let's continue this conversation both at the next workshop and over direct connections and links. If there is any way that we as the organizing team, myself, Jessica, or Sam, who some of you have been in communication with, can help to make those connections or further these conversations, please do not hesitate to reach out and ask. We are super passionate about human performance in space and are looking forward to continuing to build a robust industry and academic research network. So thank you all. I hope that you have a great rest of your Friday and a delightful weekend. We appreciate you joining us today.